Okay, here's a simple tutorial on how to use um, the architecture generation tool from the C source code for a specific example. Notice in this directory I've only got two files, traveling salesperson.c file and also an architecture file that describes some constraints. I'll show you both of those. First of all, here's the C source code. Notice that it truly is C source code. There's no unusual pragmas or macros defined up here, just general stuff. Look through it, you see the normal things like for loops, while loops, computations, array declarations, things of that sort. The compiler will consume this code just fine. The other file to look at is the constraints file. This is constraints file for a Vertex 4 FX60 device, and a similar file, architecture description file, could be generated for any FPGA. We've got a list of data components that the system can use as building blocks, also a set of constraints, slices, block RAMs, DSP48 units. This utilization aspect specifies what percentage of the slices you actually want to use in your design. And also this overhead is static resources that may be used by something else besides what your design is based around. Also, for each of these components, there's the the performance of each of these can be characterized by a fifth order polynomial that describes its resource utilization. So these columns are the coefficients for those fifth order polynomials. And this last column over here is the latency of each of the items. So that describes the only two input files that you need for your system. So in order to run this from the command prompt, all I have to do is type SATH. SATH stands for Simulated Annealing to Hardware Tool. The name of my input file, which is tsp20.c. The name of my constraints file, which is v4fx60.fpa. And then I have to specify a data width, the number of bits wide I want my data word to be. And I hit enter. And there it goes. It keeps streaming along. A bunch of stuff pops up. And this just keeps thinking. So I'm going to pause this recording and I'll come back. This will run for about 10 or 12 minutes, so I better pause it and come back once it's completed. Okay, I'm back. It looks like it's done running, and as you can see in the background, there's a whole bunch of files that were generated here. These are intermediate files. Plus it also has an output directory with all of the VHDL code. So to start with, we can look at, for example, let's look at the alter. This is a controlled data flow graph it generated for the alter processor. That is optimized to become this data flow graph, and based upon this, the Design Space Explorer generates an alter architecture that looks like this, with registers, muxes, random number generators, a modulo unit, memory, etc. Something similar takes place for the evaluate stage. Here's the non-optimized evaluate control data flow graph. Here's the optimized version of the control data flow graph. And here's a representation of what the architecture would look like. Kind of messy, but you can zoom in and look at different pieces. Once again, it's built out of the same thing: multiplexers, registers, memory units, etc. So those files are generated. Also, if you go into the output directory, it generated a whole bunch of VHDL files. So what I'm going to do is create a new Xilinx ISE project based upon this these new files that I've generated, and then we'll synthesize it and make sure that it actually behaves properly. So what I'm going to do is go here, File, New Project. I'll navigate over to where my new files were created, test cases, TSP20. Okay, give it a name. Next. Okay, add source. I'm going to go, notice that it wants to add all of those files that I just created. So I'm just going to grab them all and plop them in there. Next, finish, let it run. Pops everything up. Notice over here, we created a top-level module called main processor. Inside are all the submodules that it generated, and these are all built out of the basic blocks, the building blocks that I showed in the constraint, in the architecture constraint file. I can synthesize this. Takes a while to think through everything. Does the state machine encoding and all that stuff. And does some of its Xilinx specific optimizations. And looks like it's close to being done. Still thinking. It's quite a, if you look at through all these files, it really is quite a complicated, extensive circuit that it has to derive. So I think we're almost done though here. Okay, here we go. So here's the synthesis report that it came up with. Notice how many slices it uses, number of block RAMs, number of DSP48 units, and down here you can scroll through here, and if you notice right here, it's guaranteed to run at a maximum frequency of 167.5 megahertz, which is decent for an FPGA-based circuit. For the sake of time, I won't continue on with the implementation of design, but you can continue on with translate, map, and place and route to generate the actual bit stream and place this circuit onto an actual FPGA. So that concludes the, hold on just a second. Okay, before I conclude the demonstration, I was just reminded that we should look at the register transfer level schematic also. So I'll scroll into here, generate the RTL schematic so we can view it. There it is. Push into here. Notice that I've got a module associated with each of my large stages in the processor. I can push into each one of these. It really is a set of, this one is a set of multiplexers for the most part, it looks like, plus some memory elements. I can look at this one. Let's look at this one. If you look in here, we've got, this is a D flip-flop, a 12-bit D flip-flop. So is that, so is that. There's a control unit. What else have we got? If you look inside of this one, we've got a controller, a register, a couple of registers. There's a floating point multiplier. So you can go through these one by one, and the physical components are actually there. And if you go back here to our drawing of the different architectures, there's a one-to-one mapping between blocks in this file and what you can actually find in Xilinx at the RTL schematic level. So that pretty much concludes this demonstration. Thank you.